In this video, we continue our journey through the chemistry of carbonyl compounds, but we shift our focus considerably. For the last several videos, we've been studying the reactions of aldehydes and ketones towards various nucleophiles. Now we're going to embark on a unit where we start exploring the reactivity of carboxylic acids and their derivatives. And as you're going to see, the main mode of reactivity is actually going to be different for these compounds than it was for aldehydes and ketones. So to start with, in this video, I want to give you an overview of what I'm going to call the carboxylic acid family. So we'll talk a little bit about carboxylic acids, we'll talk a little bit about carboxylic acid derivatives, what they are, and why I'm lumping these functional groups together. Okay, so to begin with our discussion of carboxylic acids, I thought I would put up for you some naturally occurring carboxylic acids that you may or may not want to encounter. So acetic acid, you should be well familiar with. This is the main constituent in vinegar, which gives vinegar its characteristic odor. But as carboxylic acids get bigger, they actually get smellier. So butanoic acid, also known as butyric acid, is responsible for the odor of rancid butter. Hexanoic acid, also known as caproic acid, is responsible for the odor of dirty socks. This acid was actually first isolated from goat sweat to give you some idea of how nasty that must smell. And then when milk goes bad, you actually are smelling the smell of lactic acid, which is responsible for this taste of sour milk. Okay, carboxylic acids are not just smelly things. They're also important functional groups in a number of drugs. Aspirin, for example, is acetylsalicylic acid. There is another similar drug that's used in the treatment of tuberculosis for aminosalicylic acid. And finally, isotretinoin, which is the active ingredient in Accutane, the acne medicine, also has a carboxylic acid at the end of the chain. Okay, so carboxylic acids, as their name implies, are acidic. But at least based on the general chemistry definition of acids, they are still considered weak acids. Their pKa values mostly range between 4 and 5. Okay, so acetic acid, that you're well familiar with, has a pKa of 4.76. Benzoic acid has a slightly lower pKa, which means it's a slightly stronger acid. So it's got a pKa of about 4.2. And then if you add alkyl groups to the carboxylic acid, so propionic acid, also known as propanoic acid, your pKa goes up a little bit to 4.87. So what does this mean? Well, if we dissolve acetic acid in water, neutral water, only 2 molecules in 100,000 will be ionized. Okay, but this is still a much stronger acid than water, which has a pKa of 16, ethanol, which has a pKa of 16, much more acidic, and also more acidic than most other neutral organic molecules that we have encountered or will encounter in this course. Okay, so recall, as far as organic molecules are concerned, carboxylic acids are actually the most acidic, followed by water and alcohols, followed by alkynes, and then ammonia and other amines, alkenes, and then finally the least acidic, pKa of 50, would be the alkanes. So an important point that I want to make about the structure of carboxylic acids is they actually tend to dimerize as the pure liquid if they're in liquid form, or in the solid state in their crystal structures for those that are solids. And the way they dimerize is through intermolecular hydrogen bonds between the OH hydrogens and the carbonyl oxygen of a neighboring molecule. Okay, so they sort of do this head to tail, so to speak, dimerization. So these dimers will actually travel together once they're formed because there's two hydrogen bonds holding them together. They will actually travel together through the sample of liquid. That actually makes them less polar than you would expect, given that you have the C double bond O, another H. You would think that these would be very, very, very polar compounds. They're actually not quite as polar. They're still polar, but not quite as polar. And they also have a higher boiling point than you would expect just based on the size of the molecules and their functional groups present. Okay, so isopropyl alcohol has a very similar size to acetic acid. The only difference is instead of the carbonyl oxygen, you would have a CH3 in isopropanol. Okay, isopropanol has a boiling point of 82 degrees, and acetic acid has a boiling point of 118 degrees. Why is that? In order to get one of these molecules into the gas phase, you've actually got to break apart the dimer, because those dimers are helping to hold it together, and that involves breaking hydrogen bonds, which are actually fairly strong for intermolecular forces. Okay, so we've talked a little bit about carboxylic acid. Now I want to talk a little bit about carboxylic acid derivatives. The derivatives that we have to concern ourselves with are the acid chloride, sometimes also known as the acyl chloride, the anhydride, the ester, the amide, and the nitrile. Okay, now the nitrile looks kind of different. You may be wondering why it's on this list. Why did I choose these particular compounds to go on the list? Well, in general, carboxylic acid derivatives have the general structure of RC double bond OX, where X is an electronegative element. So that is true for the acid chloride, the anhydride, the ester, and the amide. Chlorine, oxygen, oxygen, nitrogen is the electronegative element. That still doesn't explain why the nitrile is on this list. Well, the further characteristics that we should be aware of are that all carboxylic acid derivatives can be hydrolyzed, broken apart with water. If they're treated with water, they get converted into the corresponding carboxylic acid, or if it's under basic conditions, the conjugate base of the carboxylic acid, which is the carboxylate anion. So a nitrile fits the bill in terms of this part of the definition. And the next part of the definition is all of them have a +3 oxidation state at the carbonyl carbon. Okay, so 2 bonds to the carbonyl oxygen and then 1 more bond to the X group gives you 3 bonds to more electronegative elements, and therefore they have a +3 oxidation state. The nitrile also has a +3 oxidation state because there are 3 bonds to the more electronegative nitrogen atom. Okay, recall that for a ketone, the oxidation state of the carbonyl carbon is +2, and for an aldehyde, the oxidation state of the carbonyl carbon is +1.